Hello everyone. In today's video, we will be diving deep into the differences between CPUs and GPUs. This video is very important because by its conclusion, you will have the essential knowledge to understand the GPU hardware architectures with a particular focus on Nvidia's designs. So let's start with the first question in this video. Can't we simply write a code and run it on a GPU to get the optimal performance? Surprisingly, the answer is no. A good understanding of every unit and every segment within the CPU is required to maximize its performance. To put it into perspective, imagine a doctor performing a surgery. Without a comprehensive knowledge of the human anatomy, without a complete knowledge of the human anatomy, the surgery could go wrong. Similarly, to unlock the GPU full potential, one must be well versed with its hardware. And this is actually the main purpose of this course. This is the aim of this course. Now, onto the core topic, comparing CPUs and GPUs. Look at these two images here. The first one on the left represents the CPU, while the second one represents the GPU. From these two images, both CPUs and GPUs seem to contain similar components or units. For example, both have DRAM or global memory. Moreover, they both have different cache memory levels. As shown here, the CPU contains 3 cache levels, L1, L2, and L3. On the other side, the GPU is equipped with 2 cache levels performing similar functions or similar tasks as those in the CPU. Next, we have the ALU unit, which stands for Arithmetic Logic Unit. This unit is responsible for executing instructions of any application. In the CPU, we have a limited number of ALU units, whereas the GPU houses hundreds or perhaps thousands of similar units called cores. Given these similarities, that we have DRAM in both of them, we have different cache levels in both, we have also ALU in the CPU and a core in the GPU, one might wonder about their differences and the reason that most systems require both CPUs and GPUs. To address this, let's examine the ALU. In a one-to-one comparison, one-to-one here means we are comparing one ALU with one core, one ALU from the CPU with one core in the GPU. In a one-to-one comparison, the ALU in CPUs are markedly more powerful and more complex than the cores in GPUs. Let's take an example to explain the term powerful in this case. When referring to a powerful ALU, we are speaking of attributes such as speed. For example, modern CPUs can operate at frequencies reaching 3 or 4 GHz. On the other hand, a 2020 released GPU, the A100 GPU from the Nvidia company, has a core frequencies ranging from 765 to 1200 megahertz. And to be clear here, 1200 megahertz means 1.2 gigahertz, which is roughly a quarter of the average CPU speed. Furthermore, ALU units in the CPUs are designed for general purpose tasks and often focus on executing a single thread quickly. On the other hand, GPU cores are more specialized, often designed to perform specific types of tasks very efficiently. Additionally, GPU cores are designed for parallelism. They are optimized to process many threads simultaneously, making them ideal for tasks like rendering graphics, where the same operation is applied to many elements in parallel. So here I want to mention that understanding these distinctions between the CPUs and the GPUs is very important. But we have another question here. How do these differences impact the application performance? After all, the primary aim, the main purpose of this course is optimizing the application performance using GPUs and parallel programming, right? So now we need to know how these differences between these two devices affect the performance of any application. Considering this, let's examine the impact or the effect of the core count differences on the application performance. Here I mean the number of cores in the GPU comparing to the number of ALUs in the CPU. Okay, so here we are going to study two scenarios. In the first, we assume most of the application instructions are dependent, meaning each instruction relies on its predecessor. To clarify this, let's draft some instructions for this scenario. We start with 3 separate instructions, each performing a distinct operation. Here, in this instruction, we add 2 values, then we multiply them in the second instruction, and finally, we use this instruction to divide them. Specifically, our initial instruction takes the values from register R2 and R3, adds them together, and stores the result in R1. Next, we multiply the value in R1 with R5, storing the outcome in R4. Now, a crucial point to note here is the interdependency of these instructions. If you observe the second instruction, it uses R1, the same register that was involved in the preceding addition. This means before we can carry out the multiplication, the addition needs to be complete. Thus, the second instruction depends on the result of the first. Similarly, our division operation waits for the result of the multiplication operation because it involves R4, where the multiplication result is stored. This method of processing is termed or is called sequential execution, which means that the instructions follow one another in a series. So in this example, we need 3 steps to execute these 3 instructions. Now, you might wonder, why not utilize multiple cores for these instructions to execute them in parallel in one step? Well, even with the 3 separate cores handling the add, multiply, and divide operations, they wouldn't operate simultaneously. The second instruction would still await for the first one, and the third would wait for the second. Thus, in scenarios like this, a few number of ALUs like those found in CPUs is ideal, especially if we have thousands of dependent instructions. This might lead to another question. If the CPUs are optimal for such processes, when would we need the GPUs? The answer lies in the nature of the operations or the instructions. While the scenario that we've discussed is best suited for the CPUs, GPUs shine brightest in situations where the instructions within an application are independent. To clarify this point, let's dive into another example. Delving deeper using our previous example of the add, multiply, and divide instructions, this time, however, there is a twist. Each instruction is independent of the others. For example, while we add values from register R2 and R3 and store the result in R1, our multiplication doesn't depend on this outcome. Instead, it multiplies values from R5 with R6 and saves the result in R4. With Such independence between instructions, if we have multiple cores available, we can assign each instruction to a separate core and execute them simultaneously. This also can happen on a large scale. For example, imagine that we have 1000 instructions with each requiring just one cycle for the execution. In this independent scenario, all instructions would be executed in parallel at once on 1000 cores, finishing collectively in just one cycle. However, in a dependent situation, it would take 1000 cycles because each instruction must wait for its predecessor to finish. From our discussion, we can deduce that CPUs are specifically designed for operations that are sequential. And sequential here means each instruction depends on a result from a previous one. On the other hand, when dealing with tasks filed with numerous independent instructions, GPUs take the lead due to their capability to run multiple instructions simultaneously across various cores. It's important to grasp this differentiation because there is a myth that GPUs are better than CPUs in all circumstances, but that is not the absolute truth. Moving on, let's explore how CPUs and GPUs coexist in most systems. Let's start with this picture here. This picture represents a general motherboard that exists in most of our computers. Here, you can observe a fan. This fan is dedicated to keeping the CPU cool and protecting it from overheating. This CPU interfaces with various components through some types of connections. For example, here we have the DRAM socket, the power interface, and notably the PCI interfaces. The PCI interfaces is very essential as it allows connection to several cards, including GPUs, network cards, and sound cards. By putting or slotting any GPU into this interface here, the PCI interface, it establishes a direct link through the motherboard pathways to the CPU. So when we put this GPU in this PCI interface, it becomes connected to the CPU. This setup here is commonly depicted in most literature, showing the connection between the CPU and the GPU. As shown, you will observe the CPU, which is connected to the GPU through the PCI interface. Alongside with the CPU, there is the CPU global memory, or what we call DRAM. Similarly, the GPU has its dedicated memory as shown here. Referring back to the previous image, the CPU's global memory, or its RAM, is positioned here in this socket, directly connected to the CPU through certain pathways or a bus connection. For the GPU, the DRAM, or the global memory, it is equipped inside this box here. I mean, we can find it on the electronic board inside this box. Okay, so the last thing that I want to mention in this slide is, while many of you might find this slide is very simple, my aim and purpose of this course is to explain each part clearly, is to clarify every part in the course, starting from the very simple basics. Okay, so now let's delve into the key components that exist in GPUs, particularly focusing on Nvidia's GPUs. The green box shown here represents the GPU card. Within this GPU, there is a crucial unit or component named the streaming multiprocessor, which is often abbreviated as SM. The term SM will frequently appear in this course, making it essential to grasp its significance from this lecture. Alongside the SM, various memory levels can be found in the GPUs, such as the L2 cache memory, and the global memory. Additionally, elements like the scheduler and dispatcher are present, and we will delve deeper into these components in the upcoming videos. Delving deeper into the SM, it is equipped with a variety of cores designed for specific tasks. Some of these cores might be dedicated to executing floating point operations, while others execute integer operations. Now, let's look at a real GPU example from Nvidia. And also, we are going to look at one of its streaming multiprocessors. So we are going to see a real example for the GPU and the streaming multiprocessor. Consider the 800 GPU, which is released in 2020. Here, this picture represents just a small part from a single streaming multiprocessor. This is not the entire SM or the entire GPU. Within this part of the SM, there is the L1 cache memory as shown here. So here I want to say that it is essential to note that while the L1 cache level is situated within the SM, inside the SM, the L2 cache memory is a part of the broader GPU. So L1 cache memory is inside the SM, while the L2 cache memory is inside the entire GPU. Okay? Additionally, as we mentioned previously, the SM houses a scheduler unit, a dispatcher unit, and several registers. In terms of execution or functional units, the SM is quite diverse. We find tensor cores specifically designed for matrix multiplication operations, floating point cores dedicated to handling floating point operations, and integer cores. There are also some special function units, and these units are designed for some specific tasks, for example, executing the log calculations. And when it comes to memory interactions, the SM features load and store units. These units are responsible for reading from and writing values or data to the memory. This detailed image provides a snapshot of only a quarter of one SM as found in the white paper of the GPU's Ampere architecture. In upcoming videos, we will delve deeper into what white papers are, where they can be accessed, and other related nuances. This particular image provides a detailed look at the specifications of the Nvidia's 800 GPU. Now I am talking about the entire GPU, not one SM. Within the 800 GPU, there are approximately 108 streaming multiprocessors. Each SM or each streaming multiprocessor contains 64 single precision cores. This means that the entire GPU, the entire 800 GPU, houses around 7,000 single precision cores, which is a very high count. However, I want you to remember this. This is only accounts for a single precision operations. The GPU also holds another 7K or 7,000 units or cores designated for integer operations. Also, if you go deeper inside the 800, you can see or find a special functional units and also tensor cores. So, I want to say here that the sheer computational power of these cores with its high count is why the 800 GPU is a central component in numerous high-performance supercomputers globally. For example, Meta Company recently announced their ambitious project to construct the world's most powerful supercomputers. If you refer to the official Meta website's article, it becomes evident that their supercomputer architecture heavily relies on the 800 system, on the 800 GPU. In the realm of recent developments, there is speculations that they might integrate the newly unveiled H100 GPU, which is launched in 2022. This is 2 years following the release of the 800 GPU or the Ampere architecture. Comparing to the 800 GPU, the H100 boasts further advancements and enhancements, and we are going to discuss both of them in this course. To highlight the significance of Nvidia GPUs, especially the E100 GPU, let's delve into the top 500 supercomputer around the world. You can find this list on a website called Top 500. This website provides detailed information about the world's leading supercomputers. As we see here in this picture, the E100 GPU exists in 3 of the top 10 supercomputers. Specifically, it is integrated into the 4th ranked supercomputer known as the Leonardo supercomputer, as well as the supercomputer ranked at number 8 and number 9. Okay? This is the last slide, so I want to thank you for delving into the world of GPUs with us, and I'll see you in the next video.